Good morning. I hope that you're having a great day. It is Wednesday. I am not here. I think I told you guys last week that this would be a day that I would be out. I forgot to remind you yesterday, and for that I apologize. A couple things before we get started. One, no phones. Put those things in your pockets, in your purses, and don't get them out. We don't want any issues. It's the first time I've been away since the last time I was away, and those phones caused problems. So I don't want those things out. Put them away. Don't test. Okay, next, I would love for you to get out two things. Your homework from last night, obviously, and also I would love for you to get out your list of squares, perfect cubes, perfect fours, perfect fifths. Get those things out. We're going to talk through these problems, and I want you to have those. In just a minute, we're going to start a note sheet. So that has either been handed out or it's going to come to you here in just a couple minutes. But we're going to do an easy part of these notes. I'm not going to try to cram the whole thing down your throat today. We're going to do the easy part. And then tomorrow, I promise, I assure you, just like always, if you're struggling, I will make sure and go over it, make sure you're all good, clear, and then we'll move into the second part, okay? So you're going to have a good day today. So let's get started with last night's homework, okay? Again, the first couple problems were very simple. I wanted you to do the evens, 9 problems, with a cube root of 512. And again, look down your column of x cubes, your perfect cubes, and sure enough, you see 512. And of course, if you scroll over to the left, the cube root of 512 is 8. 8 gets to break out of that radical because it's a whole number. Now, in this case, it did ask for me to give all possible roots. So think through this one. Is this one of those where I'm supposed to add a plus or a minus? And the answer to that is no. And here's why. This is the cube root, okay? Odd roots. If this is a positive value in here, it's only going to have one answer, and it's going to be positive. So that's why the answer is just 8, okay? Now, if we move over here to number 4, though, we have the fourth root of 1296. Again, if you look down your third column at your perfect fourths, 1296 is there. Scroll over to the left, and it is 6. But is that the only answer? And the answer to that is no, it's not. Here's why. Because this is an even root, whatever multiplies by itself to get 1296, it could have been positive, but it could also have been negative. 2 real answers. One's positive, one is negative. So to answer these questions, because it says give all possible roots, for number 4, we have to do plus or minus, okay? Now let's move along. We started off pretty simple, and we just dealt with numbers, which we've done before. This is square root. Remember, if there's no number right here, it's understood to be a 2, square root. So therefore, we're going to be looking down our list of perfect squares. Again, I hope you're looking at that paper as you do it. 63 is not on my list of perfect squares. So if I divide that by 2, so I can find the biggest perfect square that goes into it, you get 31.5. 31.5 is not on the list, but it's really just to show me, hey, where do you start? So if I look down my list of perfect squares, from 31.5 down, I start at 25. Does 25 go into 63? Of course not. Will 16 go evenly into 63? No. Will 9 go evenly into 63? Yes. That is what we use. Now the negative 8 was already out there, but we're going to break down 63 with the square root of 9 times the square root of 7, because 9 times 7 gives me 63. Now again, why did I make sure and use a perfect square? Because those are the only things that get to break out of a radical or a square root. Perfect squares. So the square root of 9 is a 3. So now that it's out of the radical, I can multiply it by the negative 8. So negative 8 times 3 is negative 24. And then that 7 just gets trapped inside. Okay? Moving down here to number 8. we see that we're now dealing with cube roots. So we're looking down our perfect cube list. Do y'all see 54 in there? I don't either. It's not there. 64, 27, it's not in between. Oh, so I don't have any way of just letting that whole thing break out. So I divide it by 2, and 54 divided by 2 is, in fact, 27. 27's on my list. So we're going to break down 54 using negative 27 times 2. Now, don't forget these need to stay cube roots of, because that's what we started with. That's what it has to stay. So the cube root of negative 27 is going to break out. Look in your list. Scroll over to the left. You see that that equals negative 3. So we can multiply 2 by negative 3. That gives me negative 6. And then that cube root of 2 remains inside. Okay, hopefully you got that one right. Number 10. 405, but we're looking at fourth roots. So I look down my list of perfect fourths. I don't see 405. And this is going to be a pretty big number. So hopefully you got your calculator out and you start dividing. 405 divided by 2 is 202.5. So I'm looking down my list of perfect fourths, and I don't see 202.5 either. So I start working my way down the list. So I do 81. Will 405 divide evenly by 81? Sure, it will. 81 goes in there 5 times. So I'm going to break 405 down with 81 times 5. Now, the fourth root of 81, if you go down your list and you scroll to the left, that fourth root of 81 is a 3. So the fourth root of 81 becomes a 3. So now I can multiply 6 times 3, and I get 18 times the fourth root of 5. Okay? Hopefully you guys understand that really well, and you got it right. Okay? Number 12. Now we start adding in some variables. Okay? So I'm going to ignore the 4 for a minute. I'm going to recognize that we're dealing with square root because there's no number here. So let's start first with our number 60. I look down my list of perfect squares. I don't see 60. So I know 60 won't come out. So I divide it by 2. That's 30. So I don't start in my perfect square list above 30. So I'm going to try 25. Well, 60 divided evenly by 25. No. Okay, keep going down. Will 60 divide evenly by 16? No. Will 60 divide evenly by 16? No. Will 60 divide evenly by 9? No. Will 60 divide evenly by 4? There it is. 4 goes in there 15 times. Okay? Now, I'm just starting with my numbers because I'm going to let that perfect square, I'm going to let it break out as a 2. And I'm going to go ahead and say, all right, 4 times 2 is 8. And I know that 15 is trapped inside. Now, I'm going to focus just on my variables. Now, remember what we said yesterday. Variables only escape in multiples of your root. Since this root is a 2, these variables can only escape in multiples of 2. So how many times will 2 go into 6? 3 times. So A comes out 3 times. Remember, that's 3 multiples of 2. Well, 3 multiples of 2 is 6. So that means all 6 of these came out. So no A is remaining inside. So then we do B. Remember, B is sitting here with an understood 1 exponent. So here's my question. How many times will 2 go into 1? Well, I mean, it won't. So if no multiples of B exist, then B is not going anywhere. It's stuck inside. So my answer is 8A cubed B, or times the square root of 15B. Okay? Hopefully you guys got that right. Let's go to number 14. Again, I'm gonna leave 2 alone. And now I'm gonna focus on my root. It's cubed, cube root. So let's look down our list of perfect cubes. Is 192 on that list. No, it's not. So we're going to take 192, and you're going to divide it by 2. And we're not going to try any perfect cubes, right, above 96. So look down your list of perfect cubes. The first one below 96 is 64. Will 192 divide evenly by 64? Bingo, we found it right off the bat. So 64, let me start over. 64 goes in to 192 3 times. Now don't forget, we still have that p to the 7th, q to the 18th. We'll take care of that in a minute. Let's start with our number. What is the cube root of 64? Look down your list of perfect cubes, find 64, and then scroll over to the left. It's a 4. So on the outside, number-wise, 2 times 4 is going to leave an 8 out there. And inside that cube root, you're going to get stuck with that 3. Remember, it don't get to go anywhere. Now we can focus on our variables. How many times will 3 go into 7? Twice. P comes out twice. Remember, that's 2 multiples of 3, y'all. 2 times 3 is 6. So 6 P's actually escaped. Well, how many were there? There were 7. 7 minus 6 is 1. So I have 1 P remaining. And last one, how many times will 3 go into 18? 3 goes into 18 6 times. So Q gets to escape 6 times. That's 6 groups of 3, which is 18. So all of those come out, so no Q's are left in. So our answer is 8p squared q to the 6 times the cube root of 3p. Now I know that seems like a lot, and maybe it is a lot. I don't know exactly where you are on this. Like obviously we can have a conversation about it tomorrow if you're struggling with it still. But to me, I feel like this should be one of the simpler things we have done. And therefore I think you guys are probably doing okay. All right, let's look at this last one that deals with cube roots. And that's negative 625. So I'm going to look down my list. And cube root of 625 is not on there. Dang it. So let's divide 625 divided by 2 is 312.5. Now all that does is just gives me a reference. 312.5. Don't look at any perfect cubes above 312.5. So I'll start with 216. Will 625 divide evenly by 216? No. Will 625 divide evenly by 64? Nope. Will 625 divide evenly by 27? Nope. Will 625 divide evenly by 8? Nope. Did I miss something here? I think maybe I did. I skipped over the one value that works. What an idiot I am. I skipped over 125. My fault. Will 625 divide evenly by 125? Yes. 5 times 125 goes into that. So we're going to simplify this using the cube root of negative 125. And like we said, it went in there 5 times. Now, don't forget about the m28th and n12th. So the cube root of negative 125, if you go down to your list of perfect cubes and scroll over, that gets to come out as a negative 5. Inside, we know we're going to be left with a cube root of 5. So we got negative 5 on the outside, we got positive 5 on the inside. Now we finish off with our variables. How many times will 3 go into 28? Now if you don't know this right offhand, just take your calculator and go 28 divided by 3. You get 9.3 repeating. That means it's going to at least go into it 9 times. So m gets to escape 9 times. Now what is 9 times 3? 27. There were 28. So if 27 escaped to give me that m to the 9th, then that means 1 remained. And then last one, how many times does 3 go into 12? 4 times. So n comes out 4 times. 4 times 3, of course, is 12. So every one of those n's came out. And therefore, my answer is negative 5m to the 9th, n to the 4th, times the cube root of 5m. I know it's a mouthful, but hopefully you guys understood it. Okay, last one that you were supposed to do for homework. And then we're going to get into our notes. which either are on their way or they're with you already. So ignore the -2, and notice we have moved into perfect fourths. So I look down my list of perfect fourths now, and I don't see 80. I see 81, but I don't see 80. So I divide that by 2, that's 40. I'm not going to try any perfect fourth above 40. Well, sure enough, the only thing I see there is 16. Does 16 go into 80? Try it real quick. It sure does. It goes in there 5 times. So we're going to use 16 times 5. We use 16 because it's the perfect fourth that goes into it, and it goes into it 5 times. So 5 is going to get stuck. 16 is going to get to escape. It's going to get to escape as, well, what is the fourth root of 16? A whole number 2. So outside, we're going to have -2 times 2. That's -4. Inside, we're going to have the fourth root of 5. Now, I'm leaving some space. I hope I've left enough. Let's get started on our variables now. How many times will 4 go into 8? 4 goes into 8 twice. X gets to escape twice. That's 2 times 4, which is 8. So sure enough, every one of those comes out. Now, how many times will 4 go into 9? Same, twice. So y gets to come out twice. But again, that's 2 times 4. That's 8. There were 9. So if 8 comes out, 1 is left. And last, how many times will 4 go into 1? Well, 4 won't go into 1. So none of these z's get to escape. It stays inside. So my answer is -4 x squared y squared times the fourth root of 5yz. So that was it. That was your homework assignment. I hope you got all those right. Hold on to that paper because I may check it to get a grade on that. But we're going to move on now, and we're going to move on to the easiest part of your note sheet that has been given to you, which is not the whole thing. I am going to give you a few problems. In fact, y'all are probably going to be mad because it's going to be 10, but you're going to have some time to work in class. So I can see you guys now starting to complain. I can already hear it, and I'm nowhere near you, but I can hear it. I can hear y'all complaining. But these are going to be so easy, you're not going to be mad, okay? So listen, what we're dealing with today is rational exponents. Rational exponents, okay? Now, we're going to write something here. When you hear rational exponents, I want you to think, and I'm going to zoom way in, I want you to think fractional. Fractional exponents. Rational exponents is fractional exponents. That means your exponents are going to be fractions. Look at all these. All of these are fraction exponents. Even the ones you can't see yet, they can be fractional exponents. Look at all these fractional exponents. Y'all see all this? Well, that's what we're dealing with today. Rational exponents, fractional exponents. So here's the other thing I want you to write. I want you to write that rational exponents can always be written as radicals. Okay? Rational exponents are another way to write radicals. Radicals is another way to write rational exponents. So that's the first part. We're going to go from one form to the next, and then we're going to go back. Okay? So that's going to be what we do today. We're going to go from one form to the other, both directions, and then we're going to save this page 2 to tomorrow. Okay? And we'll do that together. I will be back. Okay, what I'm at today had to go to. So here's how it works, y'all. Anytime you have a fractional exponent, you have a base. Okay? You have a base. You have a base of that fractional exponent. And then when you have that fractional exponent, you always have a numerator and a denominator. The numerator obviously is up top, and the denominator is in the bottom. So here's the deal. If I'm ever writing a rational exponent, a fractional exponent, as a radical, what I have to remember is the denominator of my fractional exponent is my root. Okay? So if this is 1 over n, the denominator of that fractional exponent, that is my root. So this is the nth root of whatever your base is becomes your radicand, and whatever your numerator is of your fractional exponent is what you raise your radicand to on the inside of your radical. So a to the 1 over n is the same thing as saying the nth root of a to the first. Okay? I'm going to let you take a second to just kind of process that, because that's it. That's the trick. It's very simple, really. It's very simple, really. So you just have to remember the base of that fractional exponent is inside my radical. The denominator of that fractional exponent is my root. And if this is raised to some power on the numerator besides 1, you're going to put it inside with that radicand. So a to the m over n power is equivalent to the nth root of a to the m power. So, literally, what we're doing today is we are writing these fractional or rational exponents into radical form, and then we're going reverse direction, and then you'll have some time to work on your assignment. So look at number 1, and most of you guys are already seeing this. I always like to start, once I see that it has a fractional exponent, as it does, I like to start with the root. Remember where we find the root? The root is the denominator. So what's the root? It's the 4th root of, what's the radicand? The base of your fractional exponent, x. And is it raised to a power? Well, that numerator is 1, so technically it's the 4th root of x to the 1st. As we've talked about in the past, do I have to put that 1? No. Can I put that 1? Yes. If it gives you comfort, you can. But that's it. X to the 1/4 can be written as the 4th root of x. Okay? Same with number 2. Number 2, I always like to start with the fractional exponent. I always like to start with the denominator. This is the square root of, and in parentheses in the numerator we got 15n, and all that's raised to the 1st power. Well, what happens to something when it's raised to the 1st power? Nothing. So technically, I can erase those parentheses. It's simply the square root of 15n. Now again, why didn't I put something here? Because remember, whenever the root is 2, if I don't write anything, it's understood to be square root. So the square root of 15n. All right? How about one of you guys say out loud, what or how do I write number 3? I hope you said the cube root of 24. Now, this is the only one that we've done so far that actually fits what the very end of this statement says. Simplify if needed. Simplify if needed. See, look, square root of 15, you can't break 15 down. Look at your list. It's on your, you still hopefully have your paper out. 15 is not a perfect square. If I divide it by 2, that's 7.5. There's no perfect square below 7.5 that actually goes into 15. Look, 4 won't. 1 does, but that won't help me. So I can't break this down. But what about the cube root of 24? 24 is not a perfect cube. Look at your list. If you divide by 2, that's 12. What's the only perfect cube below 12? 8. Well, 8 goes into 24. Whoops, sorry, I wrote the wrong number. 8 goes into 24 3 times. So the cube root of 8, and let me just kind of move this a little bit. I got a little bit out of, I wonder what happened right there. The cube root of 8, if you look across, is 2. So 2 times the cube root of 3 is my answer. Okay, that's completely simplified. Okay, now look at number 4. Number 4 is 7 And you see, your fractional exponent now has an exponent up top. No big deal. We're just going to start still with what we started last time. What's the denominator? That's the root. So we have the cube root of 7 squared. Well, 7 squared is 49. Now let's see if we can break down 49. Look in your list of perfect cubes. You see 49? No. Divide 49 in half. That's 24.5. The only perfect cube below 24.5 is 8, and 8 won't go into 49. So sure enough, this one's done. Okay, look at the next one. Always start with the denominator of your fractional exponent. That's the root. So we've got the square root of my base to the 7th power. Now, is this one done? No, it's not done. We talked about this yesterday. How many times will 2 go into 7? 2 will go into 7 3 times. So k comes out 3 times. That's 3 multiples of 2, which is only 6. There were 7. 6 came out. 1 is left inside. So simplified form is k cubed times the square root of k. I hope that makes sense. Okay, number 6. Number 6, we've got 3. Or I'm sorry, let's start with the denominator of the fractional exponent. This is a 4th root of 3 to the 5th power. Now, if I look up 3 to the 5th power, you would get a number that you would have to break down. But here's what I like to do instead. Treat 3 like it's an exponent. How many times will 4 go into 5? Once. So 3 gets to come out once. Now, if 3 came out once, that was 1 multiple of 4. How many of them were there? Well, there were 5. So how many 3's are left inside? 1. So the 4th root of 3 to the 5th is 3 times the 4th root of 3. I hope that makes sense. It's pretty easy. Okay, the next one, you've got, again, look at your denominator of your fractional exponents, the 4th root of, and this is a, b, in parentheses, cubed. Now, why is that important? Because both of them are raised to the 3rd power. If I'd have just wrote ab cubed, which one does it look like is raised to the 3rd power? Yeah, but it's not just b. Both of them are. So you can either write it like this, or you could technically write it as the 4th root of a cubed, b cubed, where you distribute that cubed to both. This is probably the way most people write it, but this would be fine as well. Okay, so let's look at this next one. Here we have, look at that denominator. That denominator is the cube root of, and then you've got inside of this negative 6x squared. So if I want to simplify this, I would have, again, negative 6 squared is 36. So I would have the cube root of 36, and then x squared is just x squared. So this is the cube root of 36x squared. And then the last one where we have to go in that direction, I want you to notice what is being raised to the 1/2 power? Just the 12w. The 7 stays outside the radical, which is square root. And since both 12 and w are just raised to the 1st power, it is 7 times the square root of 12w. You know what? I've got to double check something real quick. This is a cube root of 36. Is 36 in my list of perfect cubes? No. Well, did I divide it by 2? I get 18. 8 won't go into it. So sure enough, 8 is simplified. But let's look at this one. This is square root of 12. W. Well, 12 is not a perfect square, but look down your list of perfect squares. If I divide 12 by 2, that's 6. Will a value in my perfect square list under 6 go into 12? 4 will. So we're going to break this down with 4 times 3w. Because 4 times 3 gives me 12. Now, why would I do that? Because the square root of 4, it's a perfect square. It breaks out as a 2. So 7 times 2 is 14 times the squared root of 3w. That's my answer. Okay, so that's going that direction. I highlighted that one because I just want to make sure you can see the answer. That is my final answer. Now we go the exact opposite direction. Y'all ready? Exact opposite direction. So when I go the exact opposite direction, again, I'm going to start with two things. One, the fact that I have a radical means that I have a fractional exponent, right? A fractional exponent. So I like to start with, well, what's my root? 3. My root is my denominator, right? Now, remember my radicand, whatever's inside that radical, that is my base. And in this case, guys, is it being raised to any power? Nope, technically just a 1. So it's 16 to the 1/3 power. And there it is. Okay, this one. What is my root? Well, it's a 2. So my fractional exponent has a 2 in the denominator. And since both of these are underneath here, underneath the radical, I have to put them in parentheses because they're both being raised to that fractional exponent. Now, what is the exponent inside? Well, I don't have anything, so it's understood to be a 1. So xy in parentheses raised to the 1/2 power. Okay? All right, so the next one, again, always start with the root. That is the denominator of my fractional exponent. And since both of these have an exponent of understood 1, I'm going to take both, put them in parentheses, and raise it to the 1/4 power. Okay? All right, let's keep on moving. These are hopefully getting even easier for you. So look at this one. This one we could square 11 if we want, but I'm just going to leave it and rewrite it as an exponent. Start with the root. It becomes the denominator of my fractional exponent. The radicand is 11 squared. So I have 11 as the base and 2 as the numerator. So this is 11 to the 2/3 power. What do you get on 14? Well, again, start with the root. So the denominator of a fractional exponent is a 4, and it's k, and it's to the 5th. So k to the 5/4 power is the same thing as the 4th root of k to the 5th. Now this one's a little bit tricky sometimes for people. Don't let it be. Just because that 7 is on the outside raised to the exponent doesn't change where it goes. Let me explain. What is the root? Well, nothing there. It's understood to be a 2. What is underneath the radical? 3m, so I need to put it in parentheses. So that still leaves this exponent only having one place to go, the numerator. So that's 3m in parentheses raised to the 7/2. Okay, next problem. Same deal. Start with the root. That's a 4. I'm going to write that 4 in the denominator of my fractional exponent. And this whole thing, negative 2a, is being raised to the 5/4 power. Now, hopefully you notice number 17 and number 18 is a little different than that. Because every one of these values in here, they all have their own exponent. Look, 10 has an exponent of 5, a has an exponent of 3, and b has an exponent of understood 1. Same over here. 9 has an understood exponent of 1, x has an exponent of 7, and y has an exponent of 3. So when I write all these, you still start with your root. Your root here is 2. That's going to be the denominator of your fractional exponent. And then since my first radicand is 10, it's going to go alone, but raised to the 5/2 power. I do the same thing with the other terms. And the reason I have to do these separately is because they all share different numerators. See, 10 had the 5, so it's 10 to the 5/2. A has a 3, so it's a to the 3/2. And b has a 1, so that's b to the 1/2. What didn't change, though? The denominator. The denominator is 2. because that's my root. Does that make sense? I hope so. And the last one, same thing. My root, though, is 3, so my denominator is 3. And we start with 9. We've got 9 to the 1/3. We've got x to the 7/3. And we've got y to the 4/3. And that is how you write radicals as rational exponents. So whether I'm going rational exponents to radicals or radicals to rational exponents, that is how you do it. So I want you to go to your homework, and you're going to do numbers 1 through 10. 1 through 10 is your assignment. You got time to work on this right now because this video is nearing 35 minutes. You got about 10 minutes to work on this. And again, whatever is confusing to you, we will clarify, clean up tomorrow, okay? I hope you guys have an awesome day. We'll see you tomorrow.